In this video, we're going to see how to find optimal values for certain types of functions of two variables. So we're going to illustrate this technique by looking at an example problem. So suppose we want to find the dimensions of a box that has a square base, 50 cubic inches of volume, and we want it to use the least amount of material. So let's first draw a picture of this box, and then let's write an equation that shows what we're trying to minimize. So we've drawn the picture of the box. It has a square base because we designated these two sides here as both x and the height as y, and so we're trying to find the surface area of this box, so let's write a formula for its surface area. So we designate that as s of x, y, two variables. The base has area x squared. The top also has area x squared. And the sides both have, or all four have area xy. And so we're going to add 4xy for the area of the sides. So let's write that formula that we are trying to minimize s of xy in more succinct form by combining like terms. Now, we need to note that this is a two-variable problem, and we're not able to solve two-variable problems in Calculus 1. So what we need to do is change it into a one-variable problem. We're not always going to be able to do that, but in this case, the fact that we know that the box must have 50 cubic inches of volume is going to allow us to write one variable in terms of the other. So let's see how we do that. So we've written the volume base, the volume of the base times the height, x squared y is 50, and we can solve that to for y to get y equals 50 over x squared. We are then able to use the fact that y can be written in terms of x to substitute that in place of y here and change it from being a two-variable problem to a one-variable problem. So let's see how we do that on the next blackboard. So we've replaced the y with 50 over x squared, and we can then simplify that to write an equation that's only in terms of the variable x. So we've written this in simpler form. It's now a function of one variable. Notice that instead of writing it 200 over x, we've written it 200x to the minus 1, so it's easier for us to differentiate. So let's differentiate this now. Let's find our s prime of x. So we've done that, and then we know that we want to set this equal to 0 to find the critical value x. So we've changed back to the form with the x in the denominator because it's easier to solve this. We're going to move this term to the right-hand side, multiply through by x cubed and divide by 4. So let's show those steps. So first I fixed an error here. When we take the derivative s prime of x, this coefficient here should be a 200, not a 400. So we've got 4x cubed equals 200, or x equals the cube root of 50. And we want to know whether this cube root of 50 gives us the minimum value that we want, least amount of material, or a maximum. So let's see a way to use the second derivative to tell us whether we have a maximum or a minimum at this critical value. So we're going to take the second derivative, the derivative of the derivative, which is 4 minus 400 over x cubed. We're going to write it in the denominator form instead of the negative exponent form. And now we're going to look at something called the second derivative test. We know that when the second derivative is negative, the function is concave down, and that when the second derivative is positive, the function is concave up. So if we have a critical value where and at that critical value the second derivative is negative, then we know that that critical value is a relative maximum. And if we have a critical value and the second derivative is positive there, then we know that we have a relative minimum of that critical value. So what we're going to do is take our critical value, the cube root of 50, plug it into our second derivative, and hope that it comes out to have a positive second derivative so we get the minimum that we want. So let's do that. So we plug the cube root of 50 into our second derivative. Notice I've corrected the sign here. This should be a positive sign here and here. And let's note that this term is always positive, and this term here is also always positive, and so our second derivative is positive as desired, and so at the cube root of 50 we have the minimum that we wanted to find. Now we're almost finished with the problem except for a recap, but we were supposed to find the dimensions that gave the maximum surface area, so we need to find the corresponding y value. We use the fact that y equals 50 over x squared to find y, and so let's do that. So we plug 50 cube root of 50 in for x. That gives us 50 to the 1/3 squared, which is 50 to the 2/3. We simplify this power in the numerator is 3/3, so 3/3 minus 2/3 gives a power of 1/3, and so we see that the y value is actually the same as the x value, and so really this box is a cube. Okay, so let's recap what we have done. So we had a two-variable problem that we were trying to minimize, and we cannot minimize two-variable problems, so we had to turn it into a one-variable problem. The way that we did that was to use the fact that we knew the volume. That allowed us to write x in terms of y, and so we wrote that, or we saw that y equaled 50 over x squared, and we substituted that in for y. Then we could differentiate the function. We were then able to differentiate our function because it was a function of one variable only, and we got a critical value x equals the cube root of 50. We then had to determine if that critical value was a maximum or a minimum, so we used the second derivative test to do that. So we found the second derivative. The second derivative test had us determine whether at the critical value, the cube root of 50, we had a positive second derivative, which would have given us the minimum we wanted, or a negative second derivative, and we found out that, actually we fixed this as a plus sign, we found out that this expression right here was positive, and so we did have the relative minimum that we wanted at the cube root of 50. And then finally we also solved for y by substituting the critical value cube root of 50 into y equals 50 over x squared, and we found that the y dimension is actually the same as the x dimension, so the box is actually a cube. The key step in these types of problems, two-variable problems that we are not able to solve, is that we have to turn it from a two-variable problem into a one-variable problem. When we have the additional information that we need, we can do that, and that's what we would do in the majority of these types of problems. So this concludes the video on how to find optimal values for certain types of functions of two variables, those that we can turn from two variable problems into a one variable problem.